Hello, so what I'm going to do is solve that problem we didn't have time to solve in class the other day, which is the rotational motion of the pulley, but instead we're going to treat the case where it's actually accelerating and not at rest. So here it is up here, and let me grab my marker. And we're looking at this problem where we have the bucket and now it's going to accelerate. So the biggest thing is the tension that we got earlier is not the same as the bucket like we claimed earlier, because now this thing is going to accelerate downward like this. The question is asking for A and then for angular A and linear A. So if we were going to use our previous definition of relating torque and moment of inertia, it would be I alpha like this. And remember, this is the net torque on your system, so if I were to look at this situation, I would have the tension, would be the force. To make it a torque, I need to multiply by R, minus the frictional tension, this is from the previous problem, is equal to I alpha. We got I from the previous problem, but we don't know alpha. But now we don't know tension, because tension, instead of a 15, we don't have that. So this is, I'll cross it out because it's misleading. So we actually don't have that tension anymore. So in order to find this, we could actually use the linear setup, F equals ma, to help us solve this. So if you look at the free body diagram conveniently drawn right here, and assuming the acceleration is down, making it positive like this, we could set up the following equation. We'll say the weight of it is pulling it down, minus the tension equals to mass times acceleration A like this. So ultimately, when you have two unknowns, you need another equation, and as you can see, what I'm going to do is take this and plug that into here. But let's write A in terms of alpha, not in terms of A, because we want to solve for alpha. I mean, eventually we want to solve for A, so we can go either way, but let's write it in terms of alpha. So linear A is equal to R alpha, like that. So that's what I'm going to do. I'm going to replace that with that here. So I get mg minus t equals mr alpha. Just so that we have everything in terms of alpha now. So now that I have this, I can solve for t and plug it in here. So let's do that. This will move over and become positive, and I'll subtract this all, so that will become negative. So I get mg minus mr alpha equals our tension. So I'll just box this just so I can find it easier. I'm going to plug that into here like this. So actually I'll start over here since this will be a little long. So tension is now mg minus mr alpha, that's T. We still need to multiply it all by R, minus the frictional torque equals I alpha, like that. So we're almost done. I just want to get the alphas together. So first I'm going to distribute this R. So what I get is mg, and the R comes over, minus R's combined squared alpha, minus the torque by friction is I alpha. Combining the alphas, because that's what ultimately we're going to solve for, is this all comes over and becomes added. So I get mgr minus the torque by friction equals I alpha plus mv squared alpha, like that. Now, luckily there's alpha in both terms, so I actually can extract out the alpha. So what I get is alpha, I get I plus mr squared, like that. And I just factored out the alpha. And now what I'm going to do is actually divide, I left this blank, I shouldn't be lazy, there we go, let's write it in. Now solve for alpha. So alpha would be mgr minus torque done by the friction divided by I plus mr squared equals alpha. Now the cool thing about this is what we have up here is actually torques, right? This is a force times R times torque. So torque divided by these are moments of inertia equals alpha. So that's essentially good in terms of units that this does work out. What do the numbers look like? It looks like this. So the mass is 1.53 kilograms. I'm getting that from the problem. Times G times the radius, this is from the problem, 0.33 meters, minus the frictional torque, oops, that's not the units, Newton meters, that would be the correct units, divided by the moment of inertia of the pulley, which we got from the previous part of this problem, plus mass, and then we'll multiply that by the radius once again, squared. That's all equal to alpha. So alpha will equal to, if we calculate this out, 1.53 times 9.81. Sorry, I'm doing out the calculation. Oops. Give you the wrong answer. Let's delete that one, change that. Perfect. Alpha is 6.98 when we calculate this out. And this is radians per second squared. Perfect. Like just like that. Alright, and then the next part, what's the linear one? Well, we kind of already related that. A is equal to R alpha. So now that we have alpha and R, this would be 0.33 meters times 6.98 radians per second, squared like this. So let's do that. And we get a velocity, an acceleration of 2.3 meters per second squared. So that's how you can solve this pulley system using torque now to solve it. And in this case, we include the torque involved in the pulley, as before we didn't, like that. So there you have it. This is our sample problem right here. Hope you enjoyed the video.